All right, this type of problem is where we throw everything together we've done with torques and forces, right? So we're going to write, we've written force equations and torque equations separately. For this situation, to do a problem like this, we have to write torque and force equations because it's not always going to be just one or the other, right? So I have this ladder, and this ladder is in equilibrium, both static equilibrium and rotational equilibrium, right? It's not static, both translational equilibrium, right? It's not moving left, right, up, down, and it's not rotating, right? Hopefully not if you're climbing on that thing. So let's treat this thing as just like an object that's moving left, right, up, and down. Let's write the forces on it, right? So we'll say the net force in the x direction is 0. It's not accelerating. So that means let's look at all the x forces, right? So I'm going to, in something like this, I also need to define positives and negatives, right? So I'm going to call this way positive just to keep track of everything. Okay, so let's look at all the stuff. So here's this one down here, F, right? That's pushing in the positive direction. So I'll say that's positive, and I'm just drawing it like this, right? The way it has in my picture. And anything else in the X? FW, right? That's the force of the wall. So minus the force of the wall. There's my X equation. Okay. Net force in the Y. It's not accelerating up and down either, right? Hopefully your ladder's not flying up in the air. So let's do the same thing. So let's do our Y stuff. So I have normal force pointing up, so I'm going to call up positive also. So normal force is positive, minus W, which is the weight. So now I have an X and a Y equation. And now let's write an equation for the torques about the ladder, right? So why isn't the ladder doing this, right? If a ladder slid off the wall, it would kind of do that and it would rotate, right? But it's not. So that means the net torque is 0. So that means the net torque is also 0. And that equals what's trying to make it rotate about this point right here. So that's that point right there, that's where it's fixed on the ground, right? So is there anything trying to make it rotate like that? So the weight is, right? The weight's trying to make it rotate. And what else? These two are both acting at the point. So these two couldn't apply a torque because there's no R. But these two, there's an R, right? So it's going to be, I'm going to do force of the wall times R, right? Because remember, torque is FR sine theta. So the force times my R, which is L, that's the distance from the force to there. So FW times L times the sine of my angle, whatever this angle is, right? Because the sine component of this would tell me how much of L is actually pushing perpendicular. Okay, so that's going this way. Now I got to figure out, right, so I got this stuff. Now I got to figure out the stuff making it go the other way, and that's W, right? So minus W, and then it's only half of L, right? So see how W is acting at L over 2? So it's W times L over 2. And in this case, the angle that W is acting is going to be cosine of the angle, right? Because this one is on the other side of that. So, because here I use sine, right? Because if you look, sine's going to give you on here, if that's my angle, sine is that leg, so sine gives me that. But for here, my angle, I need cosine. So cosine theta. Okay, so now what I need to do is I need to figure out the angle, right? So I've written my equations. I need to figure out the angle. So let's take my x equation, right? So here's my x equation. My x equation says that the force of the wall is equal to the frictional force. And the frictional force is equal to mu times the normal force, right? Because I have coefficient of friction, so I know I got to use friction somewhere, right? So wall force equals mu Fn. Okay, I know that. Okay, so now from my torque equation, I know force of the wall times L sine theta equals W times L over 2 cosine theta. Right, so if I take this, oh look, I've got an L in both sides. Right, so the L can go away. So that leaves me with FW sine theta equals W over 2 cosine theta. And then from my y equation, I know that the normal force equals the weight. Okay, so let's start with this equation. So FW sine theta equals W over 2 cosine theta. Okay, so I'm going to swap FW. I know from here has to equal mu Fn. So I'm going to say mu Fn sine theta equals, well, I should just call it n, right? So just pretend I wrote n, because that's the way they keep it on here. So mu n sine theta equals 1/2 W cosine theta. Okay, so now I know, oh look, I know n is equal to W, right, from here. N is equal to W from this equation. So now I can say mu n sine theta equals n over 2 cosine theta, right? And that goes away because I have one on both sides. So now let's see where I'm at. I'm at mu sine theta equals cosine theta over 2, right? And so maybe you know, maybe you don't know, sine over cosine, right? If I do sine over cosine, that equals tangent. So if I divide the cosine over and move the mu over, right? So I'll divide this over. I'm going to divide sine over cosine. That's equal to tangent theta, right? And then I'm going to divide mu over to get mu to the other side. So equals 1 over 2 mu. Right? So now I have this. And I can take this and let's come over here. I want to solve for theta, right? So I can use my inverse functions. So I can say the inverse tangent of 1 over 2 times the coefficient is equal to my angle. And if you do this in degrees, not radians, you should get your answer, right? So this one, if you can write the equations, this one really wasn't terrible. Because if you can make these equations, again, all I did was substitute stuff that I know into here, right? But again, the whole concept is, can you write these equations? If you can write these, then you can do the algebra.